Hello and welcome to a new video from CHE 101. I am Cassandra Santa Ana from the Academics Committee of the Chemical Engineering Society, and in this video I will be discussing integration by parts under Integral Calculus or Cal-Eng 2. So for this discussion, I am first going to provide a brief introduction of the method of integration by parts, its general formula, the Layet technique, 3 sample problems, and at the end, a summary of the entire discussion. So let's get right into it. Now, before anything else, let's first define what integration by parts is. Basically, it's an integration technique that can be used on a function that is not integrable by simple integration. Now, as a general rule of thumb, when you have to evaluate a certain integral, first, check if it is integrable by simple integration techniques, like the power rule. If not, then try u substitution. And if it still doesn't work out, then you can try using integration by parts. So we have this general formula that we use when integrating by parts. It's the integral of u dv equals uv minus the integral of v du. In order to use it, first we identify u and dv from the original integral, differentiate u to get du, integrate dv to get v, plug these values into the right side of the equation, and then simplify to get our final answer. So remember, the first step in integrating by parts is to choose u and dv. But sometimes it's not always easy to identify u and dv in the original integral right away. However, there is what we call the Layet technique that can be helpful in identifying u. U should be chosen in this level of priority. First is logarithmic functions, followed by inverse trigonometric, algebraic, trigonometric, and exponential. Do note, however, that Layet is not a strict rule. It's just a technique. It can fail sometimes, but it is helpful in most cases. Now, to better understand how to perform integration by parts, let's now move on to our sample problem 1. So here we are asked to integrate x ln x dx. First, we have to identify u and dv. So according to the Layet technique, we should choose ln x to be u because this is a logarithmic function. Actually, whenever you have to integrate a function that contains ln, or the natural logarithm, you will almost always have to use integration by parts. Now, our dv will be equal to x dx. So now we differentiate u and integrate dv to get du and v respectively. So the derivative of ln x is dx over x, and the integral of x is x squared over 2. So that will be our du and our v respectively. Now we write the function in terms of uv minus the integral of v du. This is our general formula. This will give us ln x times x squared over 2 minus the integral of x squared over 2 times dx over x. Rewriting and simplifying both terms gives us x squared ln x over 2 minus 1/2 the integral of x dx. Solving for the integral, we get x squared ln x over 2 minus 1/2 times x squared over 2 plus the constant of integration. Now we can actually simplify this even further to get our final answer, which is x squared ln x over 2 minus x squared over 4 plus the constant of integration. So that's it for our first example. Let's move on to sample problem number 2. So here, we have the integral of arcsine x dx. Again, we first identify u and dv. So our u is arcsine x, which is an inverse trigonometric function. And our dv is whatever is left, so that's going to be just dx. So differentiating u and integrating dv, we get du equals dx over square root of 1 minus x squared, and v equals x. Now we write the function again in terms of uv minus the integral of v du. So we get x arcsine x minus the integral of x dx over the square root of 1 minus x squared. Now to simplify the second term, we can actually use u substitution. But in this case, let's use another variable since we already used the letter u. So we can let z equals 1 minus x squared, and differentiating this in order to get dz, we get dz equals negative 2x dx. Now rewriting the integral in terms of z, we get x arcsine x minus the quantity negative 1/2 the integral of dz over the square root of z. Now since the exponent of z here is negative 1/2, when we solve for the integral, we get x arcsine x minus negative 1/2 the quantity z raised to 1/2 over 1/2. Now simplifying this will basically give us x arcsine x plus the square root of z. Now if we replace z in terms of x, we get our final answer, which is x arcsine x plus the square root of 1 minus x squared plus the constant of integration. Now that's it for our sample problem number 2. And we can now move on to our last example. So for our next problem, we have to integrate e raised to x cosine x dx. Now this is actually one of the instances wherein the Layet technique does not necessarily apply, because whichever assignment we use will not necessarily produce a simpler integral. So we can just assign our u as e raised to x and dv as cosine x dx. Our du will then become e raised to x dx, and our v will become sine x. Moving on, we write the function again in terms of uv minus the integral of v du. This will produce e raised to x sine x minus the integral of e raised to x sine x dx. Now, you will notice that the integral of e raised to x sine x is not integrable by simple integration techniques, nor is it integrable by u substitution. And this means it must be solved with integration by parts as well. So let's do that. Now we solve for the integral of e raised to x sine x dx. So again, it doesn't matter which assignment for u or which assignment for dv you make, because either way you won't really produce a simpler integral. So in this case, let's just assign our u to be e raised to x and our dv to be sine x dx. Our du will then become e raised to x dx, and our v will become negative cosine x. Again, we write the function in terms of uv minus the integral of v du. So this will give us negative e raised to x cosine x plus the integral of e raised to x cosine x dx. So recall that we are solving for the integral of e raised to x cosine x dx, and this is the answer that we got when we performed integration by parts for the first time. And then, the second time we performed integration by parts was to solve for e raised to x sine x dx. So what we do next is we substitute the answer we got for the integral of e raised to x sine x dx into the first equation. So this will give us the integral of e raised to x cosine x dx equals e raised to x sine x plus e raised to x cosine x minus the integral of e raised to x cosine x dx. Now notice how the integral of e raised to x cosine x dx appears on both sides of the equation, but with opposite signs. So what this means is that we can transpose this integral and isolate it on the left side of the equation. So when we do that, we are able to arrive at our final answer for the integral of e raised to x cosine x dx, which is e raised to x sine x plus e raised to x cosine x all over 2 plus the constant of integration. So that's it for our sample problem number 3. Alright, so that'll be all our problems for today. So now we can have a short recap of our discussion. First, we said that integration by parts can be used for functions that are not integrable by simple integration techniques or by U substitution. Next, we said that the general formula for integration by parts is this. The integral of u dv equals uv minus the integral of v du. And lastly, we said that we can use what is called the Layet technique to identify u in the general formula. Layet stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. So, if you have any further questions, you can contact the Chen Academics team through email or through the Facebook link flashed on the screen. And that'll be all for this video. I hope you learned something new. Thank you for watching another video from CHE 101.